Hi there, everybody. All you physics fans out there, we're going to have a short discussion of Newton's law of universal gravitation. You might think of it as Newton's fourth law in mechanics. So we have Newton's laws of motion, but then Newton is very famous for gravity, which I'm sure you know some story. In fact, we're going to make this story time today. It's story day. What story, you might ask? Well, the story that's kind of interesting is this one. Hey, look, I just put the Earth on a balance. How many kilograms would it take to balance the Earth? This is the story of the man who weighed the Earth. Who is this man? How do we know how many kilograms the Earth is? We might say we're weighing the Earth. Actually, in scientific terms, we're massing the Earth. But we can't do it this way. We can't put the Earth on a balance. So it's an interesting story. I hope you're curious. How do we know the mass of the Earth? You can't measure it like that. It's too big. So, who is the man who weighed the Earth? Or who was he? And how did he do it? How do we know the mass of the Earth? Well, we're going to get to the answer to these questions at the end of this video, so keep watching. So this is an objective we're going to be talking about. State and apply Newton's law of universal gravitation. Newton is, of course, another story that you might have heard of, something about Isaac Newton. So let's imagine we're in Newton's shoes. I want you to kind of put yourself in his place. Suppose you've written the laws of motion, and now you are curious about gravity, and you're trying to understand gravity. There is this famous story, of course, where Isaac Newton was under an apple tree, and I'm sure you've heard this before, that an apple fell out of the tree and hit him on the head, and then he discovered gravity. If you really think about that story, that doesn't really make sense. So what exactly can we say? It's not so much that he discovered gravity, and I don't know if he even got hit on the head with an apple, but based on certain observations, Newton made conclusions or suppositions about gravity that have since been proved true or demonstrated to be correct many times over. So if you're Isaac Newton and you apply your own laws to an apple falling out of a tree, what can you conclude? Well, number one, if an apple is falling and accelerating in a certain direction, there has to be a force in that direction. So in order for the apple to accelerate down, there has to be a force down. And there's this interesting aspect of gravity that you should be aware of: free fall acceleration. Any apple that falls out of the tree would have the same acceleration. Well, if you're Newton, you make a conclusion out of that. You say, well, hey, look, if it's twice as massive an apple, so if I had one apple, it's a lot bigger than another, how can it have the same acceleration? Well, there must be twice as much force if it's going to have the same amount of acceleration. And that simple idea would lead one to conclude, hey, the force of gravity is proportional to mass. If you have a greater mass, you have a greater gravity. Notice here I put in parentheses a little formula that you've used, and you're probably already familiar with, Fg equals mg, which is based on Newton's laws. But, really this was a conclusion that Newton could have figured out just based on his idea, hey, if force is equal to mass times acceleration, the force of gravity is proportional to the mass of the object that is accelerating. But then, if you apply Newton's third law, we get an interesting result too. So, where is this force coming from? It appears to be the Earth. The apple is moving towards the Earth, so the Earth is attracting the apple. And then by Newton's third law, the apple has to attract the Earth. So if Earth pulls apple, apple pulls Earth. And there's a subtle little point here. If the amount that the Earth attracts the apple depends on the mass of the apple, wouldn't it also stand to reason that the amount that the apple pulls the Earth depends on the mass of the Earth? Think about that. Oh yeah, I guess that's right. It would actually, it's an interaction between these two masses, and if I can show that the force on this object depends on its mass, well, it must also depend on the other mass. It's an interaction that depends on mass, period. If either mass is bigger, there's a greater force, presumably. Now, Newton wouldn't have had a way to really test that second idea, but it would make sense to Newton, or anybody studying Newton's laws, that that would have to be true. And that's part of something that helped Newton figure some things out about gravity. But now let's zoom out. So Newton was interested in the moon and how the moon was moving in space. And he realized something about its orbit. Hey, wait, where did the moon go? Well, if you're Newton, you understand that the moon would not move in an orbit naturally. That's Newton's first law of motion. The moon would fly off into space if there were no force acting on it. But it doesn't do that. It's moving in an orbit. So what does that tell us about the moon? Well, that tells us that there must be a force on the moon. It can't move in a circle without a force. And that force would have to be towards the Earth if you understand circular motion, which hopefully you've already studied that, and you know there's this centripetal acceleration. Well, there has to be a force. What force is it? Well, now, you guys already know. Newton's results are kind of famous, so you're not going to be surprised by this answer, but Newton concluded that, hey, you know, the same force that's pulling an apple out of a tree is extended all the way to where the moon is and pulls the moon towards the Earth. Gravity doesn't stop at the top of a tree. Gravity doesn't stop at the top of the sky or where the clouds are. Gravity reaches all the way out to where the moon is and is pulling on the moon. Now, for us today in our modern world, we don't find that as a surprising idea, because you're taught that idea from the beginning. Like in elementary school or middle school, you already heard this idea. But at the time of Newton, nobody knew that. So this was, in Newton's time, kind of a hypothesis. Hey, you know, maybe this gravity that's pulling this apple out of this tree is also pulling on the moon. And Newton is generally credited with determining that, or at least promoting that idea and claiming it to be true. It made sense based on everything that he understood about motion and Newton's laws of motion. But then if you say, hey, Earth is exerting a force on the moon, then the moon is also exerting a force on the Earth because of Newton's third law. And if you take stock of what's going on so far, well, let's see. Earth pulls apple, apple pulls Earth. Earth pulls the moon, which is like our big rock in space. Big rock in space pulls Earth. Earth pulls apple, apple pulls Earth. Earth pulls moon, moon pulls Earth. Well, what is the Earth? The Earth is like a big rock in space, and it's going around the sun. So if the moon, which is a rock, pulls another rock, the Earth, which is a rock, the Earth, which is a rock, can pull other things like the sun, and the sun can pull the Earth. If you try to put yourself in Newton's shoes, you start to realize, hey, you know, the Earth is getting pulled towards the sun, and presumably the sun is getting pulled towards the Earth. Everywhere you look, there seems to be these attractions between these objects. And then Newton came to the following conclusion, which is kind of a mind blower if you really stop and think about it. So let's talk about what exactly is Newton's law of universal gravitation. Number one, we call it universal because Newton made an astonishing claim. Every object in the universe attracts every other object in the universe. It wasn't just the Earth attracting the apple, it was also the Earth attracting the moon, or the moon attracting the Earth, or the Earth attracting the sun. Look, the Earth is pulling on everything, but everything's pulling on the Earth. And it's little things. The apple attracts the earth. An apple has gravity. Why would the apple attract a big rock like the earth and not attract a little rock that's sitting on the ground? Well, Newton's answer to that question would be an apple attracts a rock. You can have any two objects. Look, I have in my hand here a cell phone and a pencil. Well, the cell phone attracts the pencil. The pencil attracts the cell phone, according to what that says. We can make some strange claims. I could correctly claim, hey, all of you watching this video are attracted to me. You might find that hard to believe. But according to Newton's law of universal gravitation, that's what it says. Perhaps an even more disturbing and strange idea is that I'm attracted to all of you. So, yeah, that's what Newton's law says. No matter where we are. I made this video, and you're somewhere watching this video, even right now, wherever we are at this current moment. I should be attracting you according to what this says. So if you really stop and think about it, it's kind of a mind-blowing idea. Newton didn't discover that gravity exists. Newton figured out what properties gravity has, is the way I would say it. And this is an important idea. But he went further than that, and he also determined this equation. So this is a kind of a technical part of the story. Okay, an apple fell out of a tree. Newton figured gravity out, but he figured this out. This is a very technical thing that isn't really great for story time. An apple fell out of a tree, and Newton discovered a formula, G times M1 times M2 divided by R squared. But that's what you need to know. As a physics student, this is a correct formula for determining how much gravity there is between any two objects in the universe at any time. It's a universal law. As far as we know, it applies to anything. And it's been demonstrated to be correct in many ways since it was discovered and determined by Newton hundreds of years ago. Notice there is an important value in here, capital G. Capital G has a value, a strange-looking value, strange-looking units. This is known as the universal gravitational constant. That's a big G to distinguish it from little g. Little g is our symbol for gravity on Earth, 9.8 meters per second squared. Little g is kind of like a more of a local gravity. What is gravity like in my room here? Well, it's described by the constant 9.8 meters per second squared. But gravity throughout the universe is described by this quantity, big G. We sometimes call it capital G. Anyway, this is Newton's law of universal gravitation. You're going to get practice using this. I have an example in my PowerPoint here or presentation video. Let's look at it. So suppose we had two objects. These would be kind of roughly the size of bowling balls in terms of the mass. A bowling ball is around 4 or 5 kilograms. And separated by 0.3 meters, would be roughly a foot. So I don't really have this diagram correct to scale. But what would Newton's law show us about two such objects? There should be a force of gravity. Let's calculate it. So here's how you would calculate this. Every time you use Newton's law of universal gravitation, you're going to use the same constant, capital G, which is a quantity that you might end up memorizing, but if not, you could look it up. And then we have product of the masses. So M1 times M2, in this case 5 kilograms times 4 kilograms, divided by the distance squared. Don't forget to square when you use this formula. That's a common careless mistake. 0.3 meters from center to center of our two spherical masses here. And I'm going to square that quantity. Look at the units here. Kilograms, one of the kilograms in my numerator would cancel the kilogram that's in the denominator of the constant. And then meters cubed, and I'm dividing by meters squared. So that's going to get rid of all of the meters except for meters in the numerator. And when I do this calculation, you can try this with the calculator, you get 1.48, 10 to the negative 8 kilogram meters per second squared. Now I hope you recognize that that's newtons. Hey, look, we just found a force in newtons. The big blue object would attract the little green object this amount. That would be 15 nanonewtons, let's call it, which isn't much force. But by Newton's third law, the little green object is also attracting the blue object, 15 nanonewtons. They attract each other. It's a mutual thing. It's an interaction. They attract one another, this amount, the amount that we calculate with Newton's law. Notice that's a tiny amount, 15 nanonewtons. You're never going to notice that. And that's why it's possible for Newton to be correct, that everything attracts everything. We don't notice this kind of attraction. Ordinary or everyday objects sitting around the room, they should be attracting to one another. But if you do the numbers, crunch the numbers, so to speak, you'll find that it's usually a tiny amount that we ignore because it's so tiny and negligible. But it's there, and it actually can be measured and has been measured. So we know that it exists. It's just so tiny we don't usually worry about this kind of force when we have ordinary objects like this. But let's play around with the formula. So if you look at this formula, I'm going to make some changes, and let's just talk about the kind of relationship. So Newton shows that gravity is proportional to mass. Let's suppose that I double the mass of the blue object from 5 to 10. Let's watch what happens. And think about it in our formula. So here I just doubled the mass of the blue object. If you look at this formula, if you double one of the masses, you're going to double the result of the calculation. That's a direct proportion. So double the mass of one object, my force amount doubles. And it would be the force on each object doubles. Let's double the mass of the green object. What's going to happen? We went from 15 nanonewtons to 30 nanonewtons when we doubled one mass. Let's double the other mass. Can you predict what's going to happen? Well, it's going to double the force again. So now from 30 nanonewtons to 60 nanonewtons. Now we're going to double the separation distance. If you look at that, we're dividing by r squared. So if I increase the distance, that's going to decrease the force. And this is, we're dividing by the square of the distance. Can you predict this one? If I double the distance, then squaring it, 2 squared is 4. Here we go. My force drops by a factor of 4. So if I double the distance, that's going to decrease the force by a factor of 4. And then we're back to where we started, 15 nanonewtons. Because now I have twice, each mass has been doubled. That would increase the force by 4, but I also doubled the distance. That would decrease the force by a factor of 4 if I double the distance. And then that gets me back to where we started, 15 nanonewtons. Every object attracts every other object in the universe, but if they're far apart, the force starts to get really small because we're dividing by that distance squared. This is called an inverse square law. So let's think about the inverse square aspect of Newton's law of universal gravitation. Here I have an image where I've created kind of a number line based on the size of the Earth. And imagine a person standing on the Earth, and they have a weight of 720 newtons, just as a possible value. That would be a typical value for a person. And then this would be the force of gravity coming from the Earth at the distance from its center. If we start moving further away from the Earth, that force is going to decrease by the inverse square law. So let's now double the distance to our person. Look what happened to the amount of force. It dropped from 720 to 180. And that is the inverse square law. If I double the distance to the center of the Earth, 2 squared is 4. My force of gravity would drop by a factor of 4 from 720 to 180. Our person's mass did not change, but their weight would change. So their weight is decreasing if they move away from the Earth, which probably makes sense to you. My person seems to be heading out into space, so their weight is getting less. Well, what happens if I move out to 3 times my original distance? Now down to 80 newtons. Where did that come from? 3 squared is 9. So 720 divided by 9 is 80 newtons. Notice in my diagram, my arrow has gotten tiny. And we're going to keep moving our person out, but now the arrow is going to kind of disappear because it's too small to draw. So get out to 4 times the distance. 4 squared is 16. 720 divided by 16 is 45. 5 squared is 25. 720 divided by 25 is 29, or rounds off to that amount. And then how about at 6, can you do this one in your head? So originally we started at 720. Increase your distance from the Earth by a factor of 6. What happens to the force of gravity acting on you? Do you have the answer? You can pause the video if you want to. 6 squared is 36, and that's not too bad math. 720 divided by 36 is 20. 20 newtons is not much. That's like about 5 pounds. Here, let's go on out to 10 times the distance. 10 squared is 100. Now we're down all the way to 7.2 newtons. And that's about a pound of force. So if you get that distance from the Earth, your weight has gone from 150 pounds down to a pound, roughly. So it's an interesting thing to think about. Our person is still not technically weightless if you say weight is the pull of gravity. So what has happened to our person? Well, they've followed this law, and if you graph it, it would look like this. The inverse square law is this curve that approaches 0 but never gets there. So that's kind of interesting. The force of gravity should never reach 0, but it is going to get smaller and smaller until at some point it's ignorable, so tiny it's not going to matter. Would be a curve that looks like this if you graphed it, the values in the previous problem. Now, last part of our video here, what about this value G? Where did that come from? It might surprise you to learn that Newton himself never knew the value of capital G. It was his formula. I'm sure he was confident that it worked and that it was correct. He had reasons to believe it to be correct. He could actually use his formula to model the motion of the planets and the moon, and he got results that were consistent with observations, but he never knew the value of capital G. Capital G was not determined with any sort of precision until 1798. That was much later. You know, what is that? I don't know, a couple hundred years almost from when it was determined. The first law was first arrived at. So it took a while for it to be determined, and this is a diagram of the contraption that Cavendish used. This was a technical challenge to create a system that could be used to determine the value of G. Kind of hard to tell what's going on in this diagram, so I have a simplified version of this. Let's look at it. This is called a torsional balance. And the idea is that we have these two masses at the end of kind of a dumbbell or barbell kind of arrangement. And hanging from a wire or some sort of ribbon supported, just hanging there and free to rotate. So if you think about it, it would take very little force to cause it to spin in either direction. So this thing could spin one way, it could spin the other way. It's free to rotate in any direction. But then bring in some other masses, and if Newton is correct, this tiny attraction of ordinary masses would cause that barbell shape to twist. It would cause the wire to twist. And that would move the masses closer to one another, a measurable amount. This was an observable effect. It takes a tiny amount of force to twist that wire, but these masses, the blue masses that came in here, are attracting the green masses, and that's going to twist the wire just a little bit. That's why it's called a torsional balance. And then we reach an equilibrium, and the forces are balanced. The masses, the green masses, are being attracted to the blue masses, but that's being countered by the twisting of the wire. The wire acts a little bit like a spring, a torsional spring. Once that has happened and you have all the values, we know what these masses are, we know what our wire is like, we know the distance we can measure, we can solve for G, and that is what Cavendish was able to do. He was able to make these measurements very carefully and solve for G using Newton's law of universal gravitation. That's where the value comes from, and it's a very sensitive and delicate measurement to make, but we have a pretty good idea of the precise value of G this day and age. Now, what about the way we started this video? The man who weighed the earth. You might think it would be Newton, but you would be wrong. How do we get the mass of the earth? Well, the mass of the earth is something we can solve for with Newton's law. So, for example, if we know that, say, the person in our previous example is 720 newtons, that's the force of gravity, and we know the mass of that person, we could solve for the mass of the earth. But wait a minute, in order to do that, we need the value of G. And you can't get the value of G unless you measure the force of gravity on two known masses. So that's why Cavendish, his measurement of capital G is necessary to be able to do a calculation like this. The R in the formula, by the way, would be the radius of the earth, and that was known in the time of Newton. But G was never known in the time of Newton. Newton would have been able to do the calculation. He had the formula that we need, but he didn't have the value of G. So Cavendish is the man who weighed the earth, because he's the person who determined the value of G for the first time, and that allows us to calculate the mass of the earth. Actually, it's kind of funny. We call him the man who weighed the earth. He should be the man who massed the earth, but that doesn't sound as good. So we'll just keep calling him the man who weighed the earth. I hope you enjoyed this little story. You're going to get more practice with Newton's law of universal gravitation, and I'll see you next time.